Maybe there is a connectivity issue. He'll come back.
Yeah.
Yesterday, that girl was very good,
She was asking some reasonable question actually.
and she, in fact, was really interested to learn. Hello, Nivid Chandra. You can unmute and ask any doubts if you have. Naveen?
Yes, sir.
Can you unmute Nivid and if you want, he can ask question.
Yes, sir. I already gave request from my side, sir.
Doubts
As
if you
per-
have. Okay.
Yes, sir. I have a few questions. Can you hear me, sir?
Yes, sir. Please tell me.
Sir, can you hear me?
Yeah,
Yes,
sure.
yes,
I'm
yes,
hearing
yes.
you.
Yes, sir.
Can you unmute Nivid and if you want, he can. No, we are hearing you, Nivid. Please continue.
I already gave request from my side, sir. As per-
Okay.
Can you hear me, sir?
Okay, we are hearing you. You please tell.
Okay, sir.
Yeah, sure. I'm hearing you.
One question, sir, I have. Why there's a coupling does not pass through heteroatoms?
No, it is there. A coupling is there even between heteroatoms also. Remember,
Yes, sir. My one question is, why does not the coupling pass through heteroatoms?
it passes through heteroatom also. If you remember when I introduced
I
coupling,
can't hear you.
you can't hear me?
I have problems on my end.
Are you hearing me? Others are hearing me? Then
Yeah, we can hear you.
okay,
Sir,
Nivid,
can you hear me?
I can hear you. I understood your question. I remember in one of the slides I showed you, I took an hypothetical molecule containing fluorine, phosphorus, etc., a phenyl ring. Intentionally, I took a molecule. I showed you one proton. Can you experience? You please tell.
One question, sir, I have. Why there's a coupling does not pass through heteroatoms?
That's what I understood. I understood your question. There even between heteroatoms also. No, you do one thing. There is some disturbance from your background. You can turn off something which is giving more noise
Why
there.
does not the coupling pass through heteroatoms?
I understood.
Nivid,
Remember when I introduced coupling, you can't hear me?
Nivid, you are using two devices. Switch off one.
Nivid, you switch off one of them.
You are using two devices, so
Okay, Nivid.
better you switch off one.
I can hear you. I understood your question. I remember in one of the slides I showed you, I took an hypothetical molecule.
No, it is a bouncing back. It is echo. It is echo.
It is echo. What I said, it is coming
Nivid
back.
is using two devices at a
I
time.
showed
in
you
one
one
room.
proton. Can you experience? You please tell. Okay. Nivid, are you hearing me now? I understood the question. Now you do one thing. There is some disturbance from your background. You can turn off something which is giving more noise there. Are you using two devices? Mobile and laptop? Okay. I understood your question. I'll explain. You please listen carefully. See, one of the slides I showed you in a hypothetical molecule containing carbon, phosphorus, fluorine, proton, etc. I took example of one proton and I said it can experience coupling with carbon, phosphorus, fluorine, everything. And I showed this proton can experience 10 different types of couplings. So it disappeared also.
He is using multiple devices actually, it seems.
Yeah, he is not understanding what you said. Yeah. He should switch off one.
कहाँ नितिन?
He has gone. Maybe he will log in again.
Yes, sir. Can you now hear me? There was some
Very
problem
good.
in my end.
Okay, I understand. I understood your question. Remember, I explained to you in one of the slides, there is a heteronuclear coupling also. It is not between only homonuclear coupling. I'll share this slide and I'll show you what I explained to you earlier. Can you see this slide?
Not yet, sir. Not yet.
Now, I've shared it.
Now it is shared. You can see.
You see it now?
Yes, yes.
Yes, sir.
Okay.
I can see that. I can see.
It is some hypothetical molecule. Don't worry whether it exists or not. I just wanted to show you this proton. This proton can experience coupling with all the NMR active spins in this molecule. For example, I have taken this molecule deliberately so that, to show various hetero and homonuclear couplings. See, this proton can couple to this carbon. There is heteronuclear coupling. It can couple to this carbon. There is heteronuclear coupling. It can couple to this fluorine. That is also heteronuclear coupling. It can couple to this carbon. That is heteronuclear. Coupled to this phosphorus, heteronuclear. This carbon, this fluorine, and this proton homonuclear. See, I gave you this example to show the couplings are not restricted only among homonuclear spins. Couplings will be present and a magnetization transfer takes place among all the NMR active nucleus, provided there's a covalent bond between them and they are separated by only 2 or 3 bonds. As the number of interconnecting bonds, consecutive bonds increases, the coupling strengths come down. And after 4 bonds or something, practically it is 0, except in some examples, even up to 7 or 8 bonds, you can see the coupling. That's what I said. So in this molecule, I'm showing you, you are expecting coupling among all internuclear spins here. For example, this proton can experience 10 different couplings, I told you, both homo and heteronuclear. You got this point?
Sir, yes, sir. I have understood this. My question was a little bit different. Suppose
Yes, sir.
there is ether bond. Suppose
Huh?
there is ether bond or a carboxylic group. Then you said that the 2 parts of the molecules can be treated independently. Suppose there is ether or carboxylic.
Okay. What happens in between if there is a breakage? If there is no bond, if there is no interaction between 2 protons, for example, CO, CC, something you put.
Yes,
and there's one proton here, another proton which is separated by 7 or 8 bonds. Then I said there is no interaction. Interaction is small or 0. Then you can consider as 2 different spin systems. That's what I said.
Yes,
is that your question?
Why is that? Why is that the molecule is broken into 2 parts if there is a ether or carboxylic group?
No, sir. Molecule is not broken into pieces. We consider them as 2 different spin systems because there is no interaction between them. See, if I consider, let us say, 2, I'll show you that example also.
No, let me say.
Okay, Sandeep, explain to
See,
you.
Nivid, if you have ether kind of bond,
Yes.
so there it is not restricted. There is a free rotation. So the rotation, the dihedral angle changes 0 to 360. So in between the couplings, they are not fixed. So, and also it is going beyond 3 bonds. Suppose you have CH, then again O, then CH. So it is more than 3 bonds sometimes. Sometimes it is 3 bonds also. And also it is not proper overlapping because of rotation on this oxygen which is attached. Okay, so that is why these couplings breaks there.
Or maybe something has to do with the oxygen. It is,
No. If oxygen is nothing to do, if something is which can be fixed, then it is like 3 bonds coupling. Generally, we are very.
Yeah. If a carboxylic group is there, then definitely the number of bonds will increase.
If it is more than 3 bonds, then couplings very tiny that don't appear as a, like they cannot make a bridge while transferring the magnetization one to other, like in toxy also, in cozy also.
Okay. Okay. And the other is the rotation of the bond.
Yes, yeah, rotation also bonds, that is, there is no, the coupling is making tiny, which is coupling is transit coupling.
Okay, okay, understood.
Because coupling depends on dihedral angle. If it is keep changing, the then will average will come.
See, I told you, I will show you this example with. You understand this one? For example, in this molecule which I am giving you, here I showed coupling interactions can go beyond 1, 2, 3 chemical bonds. This is a hypothetical molecule. This proton can have a coupling with this proton separated by 2 bonds. You can have coupling with 3 bonds, this proton 4 bonds, and 5 and 6 bonds like this. Supposing, Sandeep was telling you, if between these two, there's a long chain C, like that, and there are no protons between them, between this group and this group, then the long range coupling won't be visible. Very, very small. You understand? Are you there, Nivid?
I'm there. Yes, yes.
You understand what is happening? See, if the number of bonds increases, and in between, let us say some other CO, double bond, something will come, and the protons between one side of the CO and other side are separated by 4 or 5 bonds or more, you will not see the coupling. It is very, very small, negligibly small, and you will not see that in the spectrum. That's why I said,
yes,
we said there are 2 different groups. Not that, a molecule is broken. In the NMR jargon, we call it spin systems.
Yeah, spin systems are not coupled.
Exactly. There are 2 different
there
spin
is no
systems.
sufficient coupling between them, then there is no connection. So you cannot see the toxi.
Okay, sir. Thank
you. You understood?
Yeah. And sir, my other question is that you just now gave in a couple of lectures back the example of hydrogen. Yes, they split. We don't see the splitting in hydrogen or methane. The splitting between H and H.
In the methane group, CH3.
Yeah, in a methane or in hydrogen, we have to resort to isotopic labeling of one part, and then we see.
Okay.
Why in the hydrogen spectrum itself we don't see the splitting?
Okay, that is what I explained to you. If you see my lectures, hydrogen molecule, if you consider, there is a symmetry. First of all, there is a rotational symmetry, CN rotation among HH bond. Forget about that. From the center of this hydrogen bond, center of this covalent bond between 2 protons, I assume there is a C2 symmetry. These 2 protons, what are called chemically equivalent. That means these 2 come at the same chemical shift. You got it? As a consequence, the coupling between them is not visible.
Yeah.
Now, I explained why, or how you can get the coupling between these 2.
By putting one deuterium.
Correct. Molecule should remain same, but symmetry should be broken.
Okay.
How do you do that? We will replace one of the protons by deuterium. Now there is no symmetry, and molecule is same, but there is a coupling between proton and deuterium now. Deuterium is spin 1, proton is half. So this proton spectrum appears as 3 equal lines. You measure the separation between any of the 2 adjacent lines, you will get what is called proton deuterium coupling. Using this proton deuterium coupling, by knowing the gyromagnetic ratios, I can calculate HH coupling.
Okay, sir.
This is example I gave you in the case of the magnetically or chemically equivalent spins. When the couplings are not reflected in the spectrum, how do you do that? Is by what is called isotopic labeling. That's what I said. Isotopic, not labeling, substitution. Alternately, I also gave you an example. If you go to benzene, how many peaks you get in benzene? You get only 1 peak.
Yeah.
But I can tell you, homo and hetero, 1 bond, no, not 1 bond, 3 bond, ortho, meta, and para couplings are visible in the benzene. Not visible, at least it has been measured. How did they measure? With a single peak? again, this question.
Deuterium or 13C.
Exactly. You can use deuterium, and then coupling will be, for 4 or 5 bonds is very weak. Alternately, you can use natural abundance carbon-13, or you can label isotopically one of the carbons. Then what happens? The D6H symmetry is broken for benzene. So all protons, when they, for any of the carbon, if you label it, you will have a C2 symmetry now, not D6H. Then all the protons, will start coupling with the carbon, and also HH coupling will come into picture. You understand?
So yes, so my question is basically that only. Why in the symmetric case we don't see the
See,
splitting?
I tell you, see, David, you have, suppose hydrogen, okay?
Yes, yes.
If it is chemically equivalent, it's
Yes.
okay, but if it is magnetically equivalent also.
Huh.
So they have same energy separation between two spin states, like alpha and beta.
Yes, yes.
So when you see the transitions, they are of same energy.
Okay.
If they have same energy transitions and also the shielding effect is also same for them, they appear exactly at one position, all protons.
Yes, yes, yes.
In that case, so for the coupling, there should be the difference in the energy between two transitions. Then only there are another energy levels will generate, and that will here even they are generating, but whatever they will there is a down in the energy, same type will be up energy, but energy levels remain same. So because they are magnetically equivalent, they are at one position. So whatever the changes happening there, that is opposite way happening to the ground state in the excited state to compare to the excited state. So that is why we don't see any change in their chemical shift, or that means there is no coupling.
Okay, okay, sir. Okay.
Yeah, so I will show you this in a diagram. You please follow this one. Leave it. You will see what I'm going to show. I'm going to decide to explain for class.
Yes, sir. I
See,
can.
So
now
here
I
you
have
see, here you have 4 energy states of different energy.
Okay. So you understand here, I've taken 2 protons which are very well separated. They're not chemically and magnetically equivalent. There are 4 energy states of this. This I have already explained to you how we get. And now, what is going to happen? Of course, you can get a transition. Explain to you. Now, if I take the transition from this to this, expeditive transition. Here we get expeditive transition. Both frequencies are same. Only one line for X. Similarly, here to here is A. Here to here is A transition. They are different frequency, but both are identical. Both the transitions. So you have got one peak for A and one peak for X. Now I am going to bring the coupling. Just to show you, I explained this to you in the class to see how you cannot determine the sign of the coupling. I'll take one example like this. Now you are bringing into the coupling, this beta energy state goes up, alpha state also goes up. I told you why also in the class. If you listen to my class, I have said because these two are like spins, same sign. As a consequence, they are unstable. So the energy gets more because they are unstable. So it goes up. Similarly, alpha goes up. Whereas beta and alpha spins are unlike spin. They are all, one is positive, other is negative, minus half and plus half. They get more stabilized state. So it will get stabilized. The energy comes down with the same amount for both. You get the point now. So now I'm going to see this transition. So one spin.
So now you see both transitions are different energy. That's why they come as a coupling.
You understand?
If transitions remain of the same energy, there will be no coupling.
Okay. You get the point now. Here both are same.
Now there is a change in energy transition. So that is why 1, 2, 3, 4 transitions of different energy. But if there is only exactly energy difference is there, then you will see only all energy levels remain same. So that should be why we don't see couplings in the magnetically equivalent nuclei.
Understood now?
Yes, I understood, sir.
In this case, there is no coupling. They are only same frequency. This is one transition. This is one transition, same frequency. Here is one transition. here on transition, same frequency. So there are only two frequencies, no splitting because of no check coupling. But here you see energy level gets disturbed. One will become more, another will one will go down, this will go up, this will go up, this will come down, and this will come down. As a consequence, there are four different frequencies. And this is because of coupling. That's why you get splitting in the spectrum. You got it?
Yes, sir. Yes, sir. I've got it.
Now I went further for you to explain the extent of coupling. This was positive J, negative J. It's reverse, that's all. Frequencies, what will happen? This frequency and this frequency get interchanged.
Peaks are interchanged, yes.
Get interchanged. Till you get two doublets. What will happen? In the doublet, two lines will simply get reversed. One will just come to the right, will come to the left. One will just to the left, come to the right. That's all. You will not see the difference at all. That's why I said, you will not get this sign. How will you get splitting? Everything I explained using this slide. Is it clear for you?
Yes, sir. It's clear.
All right. See, this was slide I made for you to understand the sign of the coupling and everything. I think I explained for equivalence between A2 spin, A3, AB, AMX, AX, how the energy level splitting comes, everything diagrammatically explained because there's a chemistry people are there. I didn't write any quantum mechanical equations. I explained by diagrams. I don't know if you have seen carefully all my lectures. Everything I have taken. Very good, because I have taken a lot of pain.
Yeah.
I took a lot of pain to make these slides.
Yes, sir.
To make it
Do you
very
have any other
communicative.
questions, David?
My one question is very general. What is the highest frequency what is the highest magnetic field NMR in the world?
1.2 gigahertz. No, there is no theoretical limit, but there is a practical difficulty into making a magnet and everything. So right now, commercially available is 1.2 gigahertz.
Okay, sir. 1200 megahertz. Yeah.
1200 megahertz. That means the magnetic field is huge, enormous. And the cost of it is almost the budget of our Karnataka state or something like that. It is very expensive. It is of the order of some 50 or $100 million or so. Very expensive. That's why only, I think, 3 or 4 laboratories in the world have that spectrometer.
And those are not much stable also. So not like simply 500, 600 you're keeping in lab. So they are not stable also. So commercially not available. They don't offer you.
They will be very sensitive to vibrations and other thing.
That is always the for all
earlier, 1.2 gigahertz, they discharge it. And whenever they need, they charge it as it was earlier. But now they have stabilized a little bit. So kept in some laboratories. So some practical problems are there still.
It requires some skill to maintain and do use that for a specific purpose. Such a high frequency, it requires a very specific problem. You have to attend, you have to address a challenging problem of a very big molecule, very big protein like that. You can't use that for recording the CSCL3 or TMS spectrum. You are basically a chemist?
Yes, sir. I am a chemist. Yes.
Okay, very good. So any other question?
I have one request for your future lectures. You have taken too much pain to make very good slide. Can you just give one lecture on how the NMR is actually recorded?
Practical aspect?
Practical aspect. Just one lecture.
Okay. Practical aspect not in this course. In the previous course, I have covered it.
Okay. So
in one of the previous courses, I have taken 3 or 4 classes to explain what are the parameters essential to record the NMR spectrum. I didn't show how we record, but I explained it theoretically. Because if I have to show, you have to come to NMR lab,
Yeah.
Practically to show. But theoretically, I explained that.
Okay, so I can see the other lecture.
Previous course. Again, that is the 1D and 2D NMR for chemist course. You can see that.
Sir, I think you have one advanced course after this also. After
Correct.
this.
That
So
correct.
will that course be available next year for credit?
No, it is already going on parallelly.
Next year, this year I can't take because
Next year also you can take. It is every year it is there.
Okay.
Next January it will be there.
Okay, sir. It will be available for credit, I suppose.
I think so. It is already available for credit. Even this time also. Next time, I think today is the last date to register.
I can't, sir. Let me learn basics first. Then only it's better to go for advance, na?
Okay, I understand. All right.
Next year I will take that. Yeah.
Okay, fine.
Thank you. Thank you very much, sir. You have made very good slides, I can see. Thank you.
Okay. Fine. So long as you people benefit, that's enough. That's what we want finally. And if you have further questions, you can always write to us, write to Sandeep or myself. We will definitely do our best.
Okay, sir. Thank you.
There is one student by name Swati. She has asked how to calculate degenerate spin states. And there is one by name Kajpir Sheikh, student, while recording this peptide to NMR spectra, I am facing the line broadening as a common problem every time. The sample is homogeneously solubilized. To resolve this, I tried by reducing the concentration of sample. It is not resolved. There are many factors. Sandeep has already replied for it. Very good. Hello, you have already got the answer? Sandeep has replied, Kajipir Sheikh. They are not there. Anyway, they are not online, but you have replied, Sandeep. See, there is one lady by name Swati. She says, how to calculate degenerate states? We can take the example of, for example, put this simply, you have to turn off the magnetic field, find out the energy levels, all the four of them, for example, in the two spin, they will be degenerate. You will not be able to separate them out. I don't know what is that question you are asking.
I think she's asking about the energy states.
Is it how to calculate degenerate spin states? Okay, this is what we already explained to you in the Popol nomenclature and how to get the energies. I explained for 2 spin, 3 spins also. AX, AB, A2, AMX, etc. I have taken example. In the AX case, we have to consider each spin. What is the spin state? For example, alpha and beta are the two way. It is also called wave functions. Also, you have to it is also called eigenfunctions. You have to take that, and in a nuclear spin system, what happens is the basis functions are nothing but the product functions. If I have two spins, each of them has alpha and beta spin states. So if you take the product functions, you have alpha alpha, alpha beta, beta alpha, and beta beta. There are 4 different energy states. And then depending upon whether it is what is the type of spin system, AX, AB, A2, whatever it is, you can have alpha and beta beta are the 2 pure states. There is no mixing. Whereas alpha and beta alpha can be separated out, and this is they don't mix up, or there can be mixing also. As a consequence, your NMR spectrum would be different. This we cannot explain to you since you are not here online. But what you can do is you can see, I don't know, in one of the classes, I've explained to you very clearly about all these things, about how the energy level diagrams are coming for different spin system, everything. And even I calculated this in one of the classes. You can please go through that. If you have still doubts, you can write to us. And if you have specific questions, I always recommend come online so that we can explain to you. But if you are right here, I don't know whether it is clear for you or not. That is not clear to us.
Question itself is not clear.
See, if the participant is there, we can explain and we understand what she really wants.
Can I ask just one more question?
You can ask any number of questions. You have still 30 minutes.
Yeah, in 13 CNMR, we do hydrogen decoupling. Okay. But if decoupling is not done, then it will be very easy to see whether it is CH or CS2 or CS3 by way of multiplicity pattern. So we can assign the peaks a lot more easily. Whereas
Correct.
if we decouple, then assignment will be difficult.
Correct. But in the carbon, have you in this course have already discussed carbon 13 or not? Have you come to carbon 13?
Yes,
How many classes are over?
Last two lectures.
Not only that, carbon 13 takes for another 2-3 classes. Wait, at the end, I will discuss about depth in the carbon 13.
Okay.
Using the depth, you can also do the decoupling. At the same time, you can identify the carbons. Assignment will become easy.
Okay. Along with
Advantage is, if you decouple, your sensitivity will go up. You can do the experiment faster. By using an experiment called depth, you can identify what is the type of carbon. Whether it's CH carbon, CH2, CH3, etc., you can identify. In the same course, in the same class, or maybe in the next class, we will also see, you can also use what is called inept sequence to identify different carbons. That also I have explained.
Okay, I will.
I don't know whether
Nivedh,
it has.
Nivedh,
Yes, sir.
hello. Why we decouple? Actually, that is sensitivity is one reason. Other is, suppose you have separation of chemical shift by 1 ppm. Okay.
Okay.
So that is 100 hertz only on 400 megahertz in carbon. But couplings of CH couplings are order of 150 hertz, 200, 230, like nearly like let's say 75 hertz to 200 hertz.
Okay.
Depending on the dihedral angle and also the groups present there. So that there are separation between two peaks. Suppose it is only 100 hertz. And then they coupled with the 200 hertz or 300 hertz, then you will confuse. You cannot come to know which is my real peak and what are their coupling partners. So it will be very clumsy spectra because of one CS carbon will couple in 4 if it is CS3. And it will couple in it will couple in 3 if it is CH2. Okay, and coupling will be 150 hertz, let's say, common. Okay, and separation is only 100 hertz because you have 1 ppm 400 megahertz is 100 hertz. Okay, so it is not possible for you to analyze or identify your peaks, analyze the spectrum. That is why we need
with you, Dr. Sandeep Mishra.
That is why we need to decouple.
May I have a request with you, Dr. Sandeep Mishra?
Yes.
Can you give me your email address if you don't mind? Email address?
Yes, sure. I will write my email. You can have it. Okay, we can.
In case I have any doubt, I will contact you.
That is why to identify that you can do DPT, you can do coupled HSQC and many things to identify whether these are CH3, CH2 or CH other than doing in the 1D 13C, because you cannot identify at all if it is coupled with proton. It's impossible kind of things. See, this is you see here.
This one.
See, you see here, some peaks are here and they are coupled here on top. This is coupled spectrum.
Top is it?
Near 40, near 40 you see, near 30 you see, near 20. So these are will become difficult. You cannot. It is not possible to analyze the spectrum.
Look at this. This is CH3. This is one type. Okay, I can identify. What about this region?
1, 2 are okay if they are well resolved, well isolated. That is okay, but not all. It is not possible.
So we do broadband.
You see here near 55 ppm. So you know which is which coupling, which can't say.
Look at this one. It is a corresponding molecule. Very nicely you can identify what rate is one CH3 carbon. For example, there are 2 carbons here, CH carbons. You can see it like this. Easy to analyze by doing decoupling. This problem we can overcome also. That's a sensitivity also. You understand?
Yes.
And then we can identify by using depth and inept. You wait for another 2-3 classes, you will hear that.
Okay, sir. Okay. Thank you, sir.
Other questions?
Sandeep has given his email. You can write to him. Where are you from, Nivind?
Sir, I am teaching in a college in Bihar.
Bihar. Very good. Very good.
I am, sir, from actually, I did my master's from Indian Institute of Science, actually.
Oh, IASC.
But,
Very good. Very good. Which department?
Chemistry department.
Chemistry.
Yeah.
Which chemistry? Which department? There are 3 or 4 departments in
I
IASC.
was in
No?
organic chemistry. Organic chemistry.
With whom you
Professor
did your
Uday Maitra.
project?
Professor Uday Maitra.
Uday
Professor
Maitra.
Uday
Oh, then okay. Then you are very trained, so you should know all those things.
Yeah, yeah. It's a very helpful course, sir.
Very good. Thank you. You take this course, an advanced course also in the January. There, it's a bit more physics is needed for that understanding.
What will be needed, sir?
Physics background, bit more.
Yeah, no problem, sir. I think I can follow that. Yeah.
Okay, you can attend that. Next January, you can attend. If you don't need to register, you don't need to even take the exam, but the classes are going on, you can still listen to it if you want.
Okay, sir. Okay.
You can just register without taking exam. And of course, half of is over. I think 6 weeks or 7 weeks are over. Whatever the remaining is there, you can understand.
Yeah.
So anybody else, anything? Nividi is the only person who's asking question, I think. So there are no other people who should be log off? Unless Nividi has few more questions.
I think we don't have any questions.
So Nividi, you don't have any more questions, should we log off? There are no other participants logged in?
Yes, I have, no question right now. Maybe I think we will have one more session live after the course is over, right?
Yeah, it will be at the end. At the end, it will be there. But before that, you can write us. If you have.
Yeah, one more will be there next month. After 3 weeks or so, one more will be there.
Okay, so if I have any query, I will ask that time.
Sure. In the meantime, you can write to us also.
Yes. Thank you, sir.
All right. So if there are no other questions, we can wait, or if you want 1 minute, we'll wait and then log off. Naveen, are you there?
Yes, sir. I'm there.
Not Nivid, Naveen.
Oh, Naveen.
Naveen is another NPTEL person.
Yes, sir.
So now there are not many people, only one person was there. We have answered all his questions. You think, should we log off? You want to log off?
No, sir, that you have to tell, sir.
No, I am ready to log off. There are no questions means.
Then, yes, sir. Like.
But will the student write to you saying that we didn't wait or anything like that?
No, sir. No, sir. It's not like that. Like,
okay, so we
it
can
is
log
not
off.
necessary to professor to be wait. It's like it is this 1 hour we are like we have waited, and because of there is no question, we are logging out.
All right. Okay. Thank you all.
Future, if they want anything, they will ask in Google Forms.
Fantastic.
Yes.
Okay. Thank you very much. Okay. Thank you, Wilson and Sandeep.
Thank
We'll
you.
see maybe next class will be sometime after 3 weeks. Live session, we will discuss more.